Hey guys, and welcome back to Miss B's virtual classroom. I'm going to go over some things that we're going to be learning today. So one of the last transformations we're going to look at is called a dilation. And it sounds kind of like what you might think it'd be based on what you know about either science or health. So let's take a look at the definition now. So a dilation is the figure stretching or shrinking with respect to a fixed point. So when we think of stretching, we think of it getting larger. And when we think of shrinking, we think of it getting smaller. All right? So we'll have a shape on the coordinate plane, and if we're stretching it, we're going to stretch it by a certain amount, or if we're on the coordinate plane, we'll shrink it by a certain amount. So the important thing to know then is what is the amount we are either stretching it or we're shrinking it by. So the first thing you want to take a look at is the scale factor. And the scale factor is simply what are we multiplying our original point by, which is the xy. All right, so when we take a look at this, and let me just adjust the camera, this is what you're going to find. That x, in terms of x and y, we call our scale factor k. So it's going to be some number k times our x, and then some number k times our y. All right, where k is our scale factor. How much we're either stretching it or shrinking our object. Now, when we're talking about stretching, our k is going to be a whole number, okay? So that is, for example, stretching is going to be like a scale factor of 2, scale factor of 3, scale factor of 4, etc. When we're shrinking, okay, an object, our scale factor is going to be a little different. It's going to be 0.5, 0.8, etc., etc. Usually, you'll see 0.5, the most commonly. So we have to keep in mind, okay, the 0.5 is what we're multiplying it by. And if x and y are whole numbers already, it's really easy because all we have to do is we have to just split it in half, the original figure in half. So that's what a dilation is. So let's take a closer look, and I put the example 1 and 2 on the board, but let's just focus on the first one, which is, and I'm going to put it right here. Oops. Is our triangle. So we have the triangle ABC here, and the points are the following. C is at 1, 2, A is at 2, 3, and B is at 3, 1. All right. So in the example, it asks you to do a dilation with a scale factor of 2. So that means for every single point, we are going to increase it by 2. So we're going to multiply it by 2. So I'm going to just go ahead and write it down here. So we said A, B, and C. So A was 2, 3. All right. B was 3, 1. And C was at 1, 2. So when we do the prime, which is just the transformation, remember that's what it's called, we're going to adjust it by 2. And since the scale factor is 2, I'm going to multiply everything by 2. So 2 times 2 is 4, and 3 times 2 is 6. That's our A prime. 3 times 2 is 6. 1 times 2 is 2. 1 times 2 is 2, and 2 times 2 is 4. So now I have my points for the dilation, or my stretched figure. So I'm just going to go ahead and plot them. So A prime is over 4, and it's going to be up 6. So here is A prime. B is over 6, up 2. Sorry. Okay. And then, oh, 2's up here. Sorry. And then my C is over 2 up 4. So this is my C prime. And then if I went ahead and connected this with straight lines, I prefer you use the ruler, you can see that our figure has indeed grown. It has been stretched, it has increased in size. So keep in mind your scale factor and just multiply. Also keep in mind that my figure here, I use 2 blocks to represent 1, just because for me, I wanted you guys to be able to see it more clearly, and it's easier to draw with the markers. For you, 1 block, like 1 little block like this, is going to represent 1. So just keep that in mind. Mine might look like it's a little bit more expanded, but that's just because of how I set up my graph. All right, so let's take a look at our next examples. This time, though, instead of our scale factor being a whole number, it is going to be 0.5. So that means we're shrinking our object. We're making it smaller. So when I do that, I'm going to divide each of the points in half. So I'm going to list my original points first, and then I'm going to go ahead and list the primes, or my shrunk points on the coordinate plane. So M is at -6, -4. So -6, -4. A is at -2, -4. T is at -2, -6. Yes. And then H is at -6, -6. All right. So what do? I'm going to divide each of them in half. So, ooh. All right. So, obviously, Miss B needs a better setup. My M, I'm going to list my M prime, my A prime, my T prime, and my H prime here. All right. So when I do that, I'm going to divide each of them by 2. -6 divided by, or split in half, is just going to be -3, and -4 will be -2. Then -2 split in half is -1, and -4 split in half is -2. -2 split in half is -1, -6 split in half is -3. Then -6 is -3, and -6 is -3. So now I have my new points. So all I have to do is go ahead and plot them on my coordinate plane. So I go over -3, down -2, that's going to be right here. That's going to be my M prime. All right, -1, -2, that is going to be my A prime. Then -1, -3 is going to be my T prime. And then over here, -3, -3 is going to be my H prime. And as you can see, if I connect these together, it has definitely been shrunken down, and it's a smaller size of the object. So pretty simple. So then what we need to do is we need to look at a couple of rules when it comes to our dilations. So let me just erase this real quick, and I'll give you these rules. All right, so the first rule is dealing with our pre-image and image. So the pre-image and image. All right, so remember the pre-image is our image before, all right, the original, and the image is the image after. So what happens? What are the things we can observe? Well, we can observe that they are similar, however, they're not congruent, okay? They're the same in their shape. They're both either triangles or they're both either rectangles, but they're not the same size, not the same size. So that's one difference with a dilation that we haven't seen before. Before, a lot of our transformations were congruent. All right, the image still stayed the same. Okay, it was either just flipped, rotated, or slid. This one, it is changing. The next one is that corresponding angles. Well, as much as we are shrinking or increasing, that's not going to change though between our original, our pre-image, and our image afterwards, our image. They are still going to be congruent. All right, there's this proportionality to them. So, or not proportionality, but they're not going to change at all. The angle is something that's going to stay fairly consistent, because think about it. Even though my image might be getting bigger, I still have all 90-degree angles. That's not changing at all. It's the size that's changing. So then the last thing we need to look at is our corresponding sides. All right. So when I look at my corresponding sides, what am I going to look at? Well, they are not congruent because they're not the same size, like I said. So instead, they still remain parallel to one another and proportional in length. All right, so if I said this was 2 and this was 1, that means this would have to be 4 and this one would have to be 2 in order to have a scale factor of 2. This could not be 3 because then it's not proportional and it's not a true dilation. All right, so here are the notes then on dilation. Look for a second video to look at the practice problems and see how they change and what your points should be. All right, have a good day.